Let's work through this geometry problem carefully, step by step, and pay attention to the main idea, because we actually do not need to find the two radii separately. We have two concentric semicircles, meaning both semicircles share the same center, which we are calling point C. The smaller semicircle is inside the larger semicircle, and the region between them is our shaded region. We are also given a chord xy of the larger semicircle, and this chord is tangent to the smaller semicircle at point T. The entire chord xy has a length of 12 units. Our job is to find the area of the shaded region. So, let's begin by naming the two radii. I'll call the radius of the larger semicircle uppercase r, and I'll call the radius of the smaller semicircle lowercase r. Now, before we calculate anything, let's think about what the shaded region actually represents. The shaded region is everything inside the larger semicircle but outside the smaller semicircle. So naturally, its area is going to be the area of the larger semicircle minus the area of the smaller semicircle. The area formula for a complete circle is pi times radius squared. Since we are dealing with semicircles, each one is exactly half of a circle. So the area of a semicircle is pi multiplied by radius squared, divided by 2. Therefore, the area of our larger semicircle is pi multiplied by uppercase r squared, divided by 2. And the area of our smaller semicircle is pi multiplied by lowercase r squared, divided by 2. So the shaded area is the larger semicircle area minus the smaller semicircle area. In other words, the shaded area equals pi multiplied by uppercase r squared, divided by 2, minus pi multiplied by lowercase r squared, divided by 2. Now, notice something important here. Both terms contain pi divided by 2. That means we can factor pi divided by 2 out of the expression. So we get shaded area equals pi divided by 2, multiplied by the quantity uppercase r squared minus lowercase r squared. This is a very useful form because it tells us exactly what we need to find. We do not necessarily need to calculate uppercase r and lowercase r individually. Instead, all we need is the difference between uppercase r squared and lowercase r squared. So our next goal is to find uppercase r squared minus lowercase r squared. Now let's use the information about the tangent. We connect the center C to the point of tangent CT. Since T lies on the smaller semicircle, the segment CT is a radius of the smaller semicircle. Therefore, CT has length lowercase r. Now here comes an important circle theorem. When a radius is drawn to a point where a tangent touches a circle, that radius is perpendicular to the tangent line. In simpler words, the radius and the tangent meet at a right angle. Since xy is tangent to the smaller semicircle at T, segment CT is perpendicular to xy. Therefore, the angle CTY is 90 degrees. This gives us a right triangle, which will be very useful in just a moment. But there is another important fact we can use. A radius that is perpendicular to a chord bisects that chord. That means the perpendicular radius cuts the chord into two equal pieces. Since CT is perpendicular to chord xy, point T is the midpoint of xy. The entire chord xy is 12 units long, so we divide 12 by 2. 12 divided by 2 equals 6. Therefore, xt is 6 units, and ty is also 6 units. Now let's focus on the right triangle CTY. We already know that CT is the radius of the smaller semicircle, so CT equals lowercase r. We also know that ty equals 6 units. And what about cy? Since y lies on the larger semicircle and c is its center, cy is the radius of the larger semicircle. Therefore, cy equals uppercase r. So inside this right triangle, we have one leg equal to lowercase r, another leg equal to 6, and the hypotenuse equal to uppercase r. Now this is exactly where the Pythagorean theorem comes in. Remember, for a right triangle, the square of the first leg plus the square of the second leg equals the square of the hypotenuse. So we can write lowercase r squared plus 6 squared equals uppercase r squared. Let's simplify that carefully. 6 squared means 6 multiplied by 6, which equals 36. Therefore, we have lowercase r squared plus 36 equals uppercase r squared. Now we want the expression uppercase r squared minus lowercase r squared, because that is exactly what appeared in our shaded area formula earlier. So let's rearrange the equation. Starting with lowercase r squared plus 36 equals uppercase r squared, we can subtract lowercase r squared from both sides. That gives us 36 equals uppercase r squared minus lowercase r squared. In other words, uppercase r squared minus lowercase r squared equals 36. This is the key result. Notice how efficiently the geometry works here. We never had to find uppercase r by itself, and we never had to find lowercase r by itself. The right triangle gave us the exact difference of their squares that we needed for the area calculation. Now let's go back to our shaded area formula. We previously found that the shaded area equals pi divided by 2, multiplied by the quantity uppercase r squared minus lowercase r squared. From our Pythagorean theorem calculation, we now know that uppercase r squared minus lowercase r squared equals 36. So this is where we substitute that value into the formula. The shaded area equals pi divided by 2 multiplied by 36. Now simplify. 36 divided by 2 equals 18. Therefore, the shaded area equals 18 pi square units. And that is our exact answer. If we want a decimal approximation, we use pi approximately equal to 3.1416. Multiplying 18 by pi gives approximately 56.55. So the shaded region has an area of 18 pi square units, or approximately 56.55 square units.